Today we'll continue discussions of liquid-liquid equilibrium, and I wanted to go back to a question that I initially asked in the last class, which was conceptually, why does liquid-liquid equilibrium occur? And at first glance, if you look at a system that's in liquid-liquid equilibrium, if you look at a bottle of salad dressing that's in your fridge, it doesn't really make a lot of sense, right? Why should a liquid mixture phase separate into two separate liquid phases? Because after all, this system looks like it is more orderly than a system that is mixed together, and therefore isn't the entropy of this system decreased, of this system lower than a mixed system? And the answer is yes, right? This is a lower entropy system, but also remember that that isn't the whole story. Remember, the universe tends toward higher entropy, but it's not actually entropy that is the final deciding factor. Remember, what the universe actually wants to do is minimize the Gibbs free energy. So what is the definition of Gibbs free energy? Gibbs is U minus TS. Wait, scratch that. Gibbs is H minus TS, and H is U plus PV minus PV. H is U plus PV. So therefore I can write that Gibbs is U minus TS plus PV. All right, so what I'm looking at are the contributions from this internal energy term and this entropic term. So remember, if I want Gibbs to be negative, right, I'm going to have two seemingly opposing terms here, right? There's internal energy and also entropy. So if a system, so say you mix up your bottle of salad dressing and it looks like one phase, it's not one phase, but say that it is, and the system kind of has to decide whether or not it wants to phase separate or not. It is going to increase its entropy. I'm sorry, if it phase separates, it is going to decrease its entropy. So S would be going down, which would make this term, this minus TS term, go up, right? Because you're subtracting a lesser number. So that would force the Gibbs free energy to increase, which would seem like it doesn't want to do that. All right, so the answer here is that by phase separating, it lowers the internal energy by more than the entropy increases. So let me write that down. So once again, a seeming decrease in entropy, in other words, the system is more orderly as two liquid phases. It doesn't seem like that should happen spontaneously because the universe tends towards disorder. However, the system is actually more stable this way because its internal energy is less. So now let's look at why would the internal energy of a system be less in two liquid phases as opposed to one. Well, let's say we've got our favorite salad dressing example where we've got water and oil. So if it's H2O, we know from experience in chemistry class that this H2O is going to form hydrogen bonds with itself. So let's denote hydrogen bonds with gold and water molecules as red. And when water is just pure, it's going to hydrogen bond all over the place, right? And hydrogen bonding is good for stability. Hydrogen bonding is going to decrease the internal energy. Hydrogen bonds decreases internal energy. Right, in general, chemical bonds take the system from a higher energy state to a lower energy state. What happens now if you introduce some oil into this mixture? So first of all, what molecule is oil? There is no one specific molecule. Let's just say it's a long chain hydrocarbon like octane or nonane or something. Right, this molecule is not going to hydrogen bond with itself, nor will it hydrogen bond with water. In fact, if you insert this into the mixture, then it's going to get in the way of some of this hydrogen bonding that's going on between the water. So if water and oil were to exist as a one complete phase, then you wouldn't have as much hydrogen bonding in the water mixture because there'd be these other oil molecules in the way. Therefore, the overall internal energy of the system would increase in relation to just pure water because there would be less hydrogen bonding. So in this case of the water and oil, it's actually more helpful for it to separate into two separate phases such that the water can be by itself and happy and hydrogen bonding with itself, and the oil can be by itself and happy and not hydrogen bonding by itself. I'm sure with the current political climate, there's a political analogy to be made here, but I don't want to make that analogy. I'll just leave it at that and say that there's a way that you could think about that in those terms. And I don't want you to get the wrong idea. I don't identify with one party or the other, nor do I want you to know what my political beliefs are. I am squarely in the why can't we all just get along camp. So I guess I'm not the biggest fan of liquid-liquid equilibrium because of what it represents, but well, not that it represents that. Again, I'm rambling or just trying to make a joke or analogy that's not working too well. So I'm going to pause and then we'll talk about equilibrium criteria for liquid-liquid. Now, temperature and pressure play a role, so it's not just entropy that is in this term, but there's a temperature as well. So the fact that temperature is here as well means that as I increase the temperature, this TS term is going to increase, meaning I'm subtracting a larger number. So as temperature increases, this entropy term becomes more and more important, right? So as temperature increases, you have less and less likelihood to phase separate because the decrease in entropy that occurs with phase separation won't be what would be too, what am I trying to say here? Maybe it would help if I write it. All right, I've clarified it in my own head. So as temperature increases, the magnitude of minus TS is going to become more negative. So therefore, it becomes even more important for the system to maximize its entropy, right? Because it wants this TS term to be as large as possible, meaning that it is as most negative as possible. Right, so as T is increasing, it is going to decrease the Gibbs free energy, and it means that the system would phase separate less readily. Also note that pressure plays a role here, but as is the case for so many other examples, pressure has a reduced role in relation to temperature, but there is still some pressure dependence. So once again, this manifests itself in the phase diagram, which I drew last time. So for a generic liquid-liquid equilibrium example, the phase envelope would look something like this. Remember, there's the stable region and the unstable region, where T is plotted as a function of X or Y. I mean, just X, right? Just X, not X and Y. It's X of phase 1 and X of phase 2. All right, so this is, you can see this in this diagram as well. So say I have a composition of X1 that is there. At temperatures that are low, I'm going to tend to be in the unstable region, which means I'll phase separate. But if I increase the temperature to increasing and increasing levels, so T2 is still in the unstable zone and it's going to phase separate. But say I increase the temperature even more to a T3, now I'm outside the unstable zone, I'm in the stable zone, and my system will not phase separate. I'll have one liquid phase out here and two liquid phases inside. All right, but this is not what all phase diagrams look like for liquid-liquid equilibrium. This is a majority of them because this is the situation that happens most often, and there's an analogy to be drawn here between a minimum boiling versus a maximum boiling azeotrope. So I could also have a phase diagram for liquid-liquid equilibrium that looks like this. So T and X would be on the x-axis where I have a minimum now. So still the same thing where I have a stable zone and an unstable zone. But now it looks like I'm contradicting myself because here, if I decrease the temperature, now I can get to the zone where I'm stable for the entire range of composition. So what's going on here? Remember, this term is the upper critical solution temperature, the temperature beyond which I cannot have two liquid phases. So the conceptual explanation of this is while some systems have reduced hydrogen bonding upon mixing, some systems have increased hydrogen bonding upon mixing. So one example of that is given in the Dahm and Visco textbook. glycol ether water system. So just by looking at the molecules, you can kind of guess that propylene glycol and propyl ether is not going to hydrogen bond with itself because it's such a big clunky molecule, right? It's hard for two molecules to align themselves such that it can hydrogen bond. Let's see if I can draw this properly. Hydrogen bond to another molecule like that, right? These big tails of the molecules are going to bump into each other, and there's not going to be much hydrogen bonding, right? So this does not hydrogen bond with itself. But we know water is a hydrogen bonding machine. It'll hydrogen bond to a lot of stuff, right? Water is a small molecule, so it can hydrogen bond. I know my hydrogen bonds are supposed to be dashed. Right now, if you mix propylene glycol and propyl ether with water, water and propylene glycol are going to cross hydrogen bond with each other. So water molecules have no problem hydrogen bonding with this propylene glycol molecule. Right? So with that in mind, you might think, well, why would they ever phase separate them? Because doesn't this make it seem like the lowest energy state would be the one with the most hydrogen bonding going on? The answer to that is that water is like the popular kid in high school, where the water could hang out and hydrogen bond with the propylene glycol and propyl ether, but it really wants to hydrogen bond to itself, right? The hydrogen bonds between water molecules are much more energetically favorable than cross hydrogen bonds. So I'm going to clarify those thoughts by writing it. So once again, we've got cross-species hydrogen bonding, but it will still phase separate this particular system for high concentrations of water, because the water is going to want to be in its own phase to hydrogen bond with itself, because that's more energetically favorable than performing the hydrogen bonding with propylene glycol. So that's going to wrap up this video. In the next video, we'll talk about the phase equilibrium criteria and the stability criteria for liquid-liquid equilibrium.